Okay, guys, so I'm kind of going through this next one using the same mentality that I talked about earlier with the easier approach. So what I'm going to do is I'm actually going to look at example 5 in light of, is there an easier way that we can substitute in without solving for t? Okay, because yeah, we could solve for t by doing the cube root of both sides for the x1, or we could solve for t by dividing by 3 and then doing e to both sides, but both of them kind of complicate things. So I'm going to look at this and see, all right, new set of eyes, is there a way that I can substitute in to get rid of the t's, but have it only in terms of x and y and not having to solve for t? So first thing I'm going to do is I'm going to look at y, and I see there's a 3 in front of the log. So I can take that 3 and I can relocate that to the back. So it would be y equals ln t cubed. All right, and now when I look at this with fresh set of eyes, I see t cubed right here. I see t cubed right here. I can substitute in not just for the t, but I can substitute in for t cubed with x. So I can write it as y equals ln, not of t cubed, but of x. And now it's all in terms of x's and y's, no t's, done and done. Okay, and that's it. All right, on to these ones where we have rectangular equations. We're looking for rectangular equations when we're given parametric equations. This is what we've dealt with in the past couple chapters ago, where we were dealing with the unit circle. We found that x is equal to cosine of theta and y is equal to sine of theta. So I started out with this one just to kind of connect concepts for you guys and whatnot. So one of the options we have, what we were doing before is solving for t. So what we could do here is solve for theta. And the way that I would get rid of theta is with cosine inverse. Cosine inverse. So I would have theta equals cosine inverse of x. Ugh, that is not looking nice, because then I would have to plug in cosine inverse x here. So it would be sine There's got to be an easier way. So I'm going to erase that. Nope, 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 nope. Not happening. There's got to be an easier way. And yes, there is. One of the things that we can look at is the fact that when we have sine and cosine, we learned a little equation with sines and cosines that we're going to revisit, which is the fact that sine squared plus cosine squared is equal to 1. So we can use that idea, and what I can do is I can get my two equations. Oops, scrolled a little bit too far. I can get my two equations to be equal to cosine squared and sine squared by squaring both sides. And then I can substitute in. So if I have sine squared plus cosine squared, I can actually write that as sine squared is equivalent or equal to y squared plus cosine squared is equal to x squared. And that is all equal to 1. So now there's no more third variable, which is theta. So I have x squared. I'm going to just write it as x squared plus y squared equals 1. And that is, dun, 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 a circle. Oh my goodness, the unit circle with a radius of 1, right? Oh, wow. It all comes full circle. Oh, math jokes. All right, so that is our equation. All right, so moving along and away from that joke, we've got same idea, but a little spin to it. X equals 3 cosine theta. And y equals 4 sine theta. So I'm going to once again refresh my memory or recap that sine squared plus cosine squared is equal to 1. So first thing I need to do is get the sine squared and the cosine squared by themselves. So I'm going to divide both sides by 3. So I get x over 3 equals cosine squared. Oh, sorry, not cosine squared, not yet. Whoop, whoop, jumping the gun, jumping the gun. All right. And then divide by 4. So y over 4 equals sine of theta. I keep wanting to say squared. All right. So now I want it to be squared, so I'm going to square both sides. So now when I square the right side, I square cosine. When I square the left side, I have to square both the numerator and the denominator, right? Because if I had it as x over 3 and we're squaring it, we distribute the squared in. So I'm just kind of shortcutting and squaring both of them in one step instead of writing it out like that. So it's going to be x squared over 9 is equal to cosine squared. And then we have squaring the right side, and we would have to square both the numerator and the denominator. So I get y squared over 16 equals sine squared. All right, now we substitute in for sine squared, which is y squared over 16 plus cosine squared, which is x squared over 9 equals 1. So I've got x squared over 9 plus y squared over 16 equals 1. That's not a circle, but that equation is familiar. It is an ellipse because my numbers underneath the x and the y are not equivalent. So it's an ellipse with the center of 0, 0. From the vertical, it goes up and down 4. From the horizontal, it goes left and right 3. Okay? So that is something that we've seen. All right, next one. Ooh, we've got x equals 5 secant theta and y equals 2 tan theta. All right, so sine squared plus cosine squared is not going to help me here because these are secant and tangent, but there is a Pythagorean identity that we did learn, which was tan squared plus 1 equals secant squared. So I'm going to use that one because we've got secant and tan, so it makes sense to use that one. So, whoop, I don't know how that just scrolled down. All right, so we've got, for this, we want to square secant and square tangent. So first thing we got to do is get the secant by itself, divide by 5. So we've got x over 5 equals secant theta. Divide by 2. So we've got y over 2 equals tan theta. All right, now we want to square, so we square the right side, and then we have to square both the numerator and the denominator. So we get x squared over 25 equals secant squared. And then we've got square the right side, square the left side, both the numerator and the denominator. Y squared over 4 equals tan squared theta. All right, so now we're going to substitute in. So tan squared is y squared over 4 plus 1 equals secant squared is x squared over 25. All right, so this looks kind of familiar, except for like all of these conic equations where we had ellipses and hyperbolas, we talked about getting it equal to 1. So I'm going to just bring this y squared over 4 to the other side. So I've got x squared over 25 minus y squared over 4 equals 1. So now it's in standard form, and that is not an ellipse this time because it's a subtraction. It's a hyperbola with my center at 0, 0. And it's opening left and right. Okay, so it's horizontal transverse axis. Okay. All right, last one. We're back to cosine and sine. So I'm going to jot that down once again. Sine squared plus cosine squared equals 1. All right, so first thing we got to do is get the sine squared and the cosine squared by itself so that we can, the sine and the cosine by itself so we can then square it. So I'm going to minus 2. So I get x minus 2 equals cosine theta. I'm going to add 1. And then y plus 1 equals 3 sine theta. And then divide by 3. So I get y plus 1 divided by 3 equals sine theta. So now I square both sides. And then I square both sides, both squaring the numerator and the denominator. So I get y plus 1, and I'm leaving it with the parentheses squared, over 9 equals sine squared. All right, so let's fill in. Sine squared is y plus 1 squared over 9, plus cosine squared is x minus 2 squared equals 1. And then I just kind of rewrite that slightly. X minus 2 squared plus y plus 1 squared over 9 equals 1. And that is my rectangular equation. It is an ellipse. And in this case, it's an ellipse centered around 2, negative 1. It's going to be a vertical, it's longer in the vertical because it goes up and down 3 and right and left 1. Okay, and that's it for these notes. Go ahead and try part 2 now.